So please welcome Jake Lowenstern to talk about Yellowstone.
All right, well, thank you very much. Everybody here okay? I mean, you can hear me, that is. Great. Well, for the next hour or so, we're going to talk about Yellowstone. And so we'll just get into it. Yellowstone, for those of you who haven't been there, it's in the northwest corner of Wyoming, over here, kind of about 1,000 miles to the northeast of us here. And it's a pretty big park. It's about 9,000 square kilometers, something like 3,600 square miles. It's a pretty big area, and for this Bay Area audience, it might be useful to look at Yellowstone relative to the Bay Area itself. So that's Yellowstone National Park. The pink line in the middle here is the caldera. We'll talk more about that, but the outline of the park is here. So it stretches pretty much from the south, from San Jose up to San Pablo Bay, and from Bolinas all the way over to Pittsburgh. So it's a big park, and so when we talk about the things that happen at Yellowstone, you kind of have to think a little bit big. Now, Yellowstone is many things to many people. It, of course, is the first national park in the United States. It was also the first national park in the world, and it started a trend of humans trying to preserve their wild places and their special places for the benefit of future generations. And so Yellowstone's a really special place just from that standpoint alone. Of course, it was preserved primarily because of the amazing geothermal features that are there, the geysers, pressurized boiling water, boiling groundwater system. It's spectacular Rocky Mountain scenery. It's world-class fly fishing. It's a charismatic megafauna, as they're known. Lots of animals that have a place to breed because we have such a special, large, wild wilderness area for them to hang out in, where they're free from hunters and other problems that we often have with our civilized society. Of course, more and more lately, Yellowstone has started to be known as the supervolcano. And along with that, we get a lot of crazy publicity and articles in newspapers, often highly exaggerated and very frequently with a great deal of misinformation. So we're going to try and cut through some of that today and see what really has happened at Yellowstone, what's possible at Yellowstone. And we're going to do that starting out really looking at what we know about it and going through a short history of the park and our understanding of the geology and the volcanology of it. We'll then talk about the primary hazards, geologic hazards, and their relative probability, what's more likely than other things, what's actually happening right now. How do we go about monitoring Yellowstone? What are the techniques that we use and what do we learn? And then at the end, a little bit more about the prospects for future activity. And any of those who want to stick around, we can do plenty of questions and answers if you're still awake. All right, so originally there wasn't a whole lot known about Yellowstone except the legends of the Native Americans and the tall tales told by the trappers. Jim Bridger here talked of petrified forests with petrified birds singing petrified songs. And he talked about rivers that raced downhill so fast that the river turned warm on the bottom. And, but there wasn't a whole lot of cold, hard facts. Congress finally put together a whole series of expeditions to explore the various parallels. And Ferdinand Hayden was one of the people who ran the expedition that went through Yellowstone in 1871. These are the groups that eventually got the United States Geological Survey started about 10 years later. Hayden brought along William Henry Jackson, a photographer, and Thomas Moran, a painter, to help document what they found in the area. They collected samples, they documented what they were seeing, and they did it through both the photography and the painting. Those materials went back to Washington, and they were really instrumental in having Congress set aside Yellowstone as a national park. Hayden also figured out quite a bit about the geology. He recognized that this was a volcanic area. And so here, when he was looking out from Mount Washburn out over the terrain, he said it is probable that during the Pliocene period, the entire country, drained by the sources of the Yellowstone and the Columbia, was the scene of a great volcanic activity as that of any portion of the globe. It might be called one vast crater made up of thousands of smaller volcanic vents and fissures, out of which the fluid interior of the earth, fragments of rock, and volcanic dust were poured in unlimited quantities. Indeed, the hot springs and geysers of this region at the present time are nothing more than the closing stages of that wonderful period of volcanic action that began in tertiary times. So he recognized this was a volcanic area. He recognized that it was not too long ago in the geologic past that it was active. He put it a little bit older than it actually is. And he also recognized that the hot springs and the hot water are in some way related to that volcanic system. He and his colleagues camped on the north side of Yellowstone Lake, and they experienced another remarkable thing that we know about Yellowstone is that there's a lot of earthquakes there. They experienced what we now call an earthquake swarm, where they were awakened in the middle of night by a series of shocks that woke them up, woke the horses up, and were shaking the trees. And this is a little quote from Albert Peel, one of the people on the expedition. Philetus Norris was the second superintendent at Yellowstone, and he had the good fortune of witnessing a hydrothermal explosion, sort of a geyser gone bad, where rocks are thrown out into the air. And he has a great quote here, where the pool was considerably enlarged, its immediate borders swept entirely clear of all movable rock, enough of which had been hurled or forced back to form a ridge from knee to breast high at a distance of from 20 to 50 feet from the ragged edge of the yawning chasm. So very alliterative quote, and so this is a hydrothermal explosion, something that we'll talk about later on tonight. And then Thomas Jagger, who later founded the Hawaiian Volcano Observatory, went to a place called Death Gulch and saw 7 grizzly bears that had imbibed a bit of poisonous gas, and he wrote that the poor creatures are tempted one after another into a bath of invisible poisonous vapor, where they sink down to add their bones to the fossil records of an interminable list of similar tragedies dating back to a period long preceding the records of human history. These guys knew how to write back then, and they also made a lot of great observations. So we knew there's a lot of gas coming out of Yellowstone, there's earthquakes there's all these unusual hot springs, it's a big volcanic system. And so the stage was set. It wasn't really, though, until the 1960s when sort of a modern perspective on Yellowstone came to pass. And this is Bob Christensen, who works here. He's retired now, but he works out of here still occasionally, out of the USGS in Menlo Park. And he spent much of his career working at Yellowstone. And over here, he is a picture of a thin section, what we call a thin section of the Logwood Creek tuff. Now, I'll explain that in a second. Tuffs, that's a word for a kind of rock that had been known to be present all around the western U.S. And in the 1950s, a guy named R.L. Smith out of the USGS in Reston has started doing a lot of work on this particular type of rock. They're fragmental rocks, and they contain crystals, and they contain a lot of glass. And so in this example from Yellowstone, here's a little glass shard. Well, the glass is quenched silicate melt. It's the melt that's present in a volcanic eruption. Bubbles form as gas comes out of solution when the eruption is starting. The material is going into the air, and the liquid quenches into glass. The bubbles break and form little shards of glass that are swept along in very violently moving, very hot clouds that fill in valleys and are called tuff, or ignimbrite, also called pyroclastic flow. In this case, there's such a thick amount of material that gets deposited, and it's so hot that it starts to weld over time. It condenses, it's very heavy, and it pushes down on itself, and all the little glass shards tend to get stretched out and aligned, and that's what you can see, these little shards that are wrapping around this crystal, which is a much tougher and less warm, less pliable material than all the glass shards that are around it. Anyway, these kinds of rocks, the welded tuffs, are evidence of massive volcanic eruptions. And so Chris was able to find not just one at Yellowstone, which they knew about, but he found out that there were 3 separate eruptions that had happened relatively recent in the geologic past. There was the Lava Creek tuff, which he mapped out in green here. So this is a map of the area that how it would have looked 640,000 years ago, right after the eruption of the Lava Creek tuff. And preceding it was the Mesa Falls tuff, and before that was another very, very large eruption, the Huckleberry Ridge tuff. And so the material comes out and moves down valleys, and sometimes is many hundreds of feet thick in the valleys, and it completely fills in this area here, which is called the caldera. Now, in the case of the Lava Creek Tuff, there's 1,000 cubic kilometers of material that got taken out of the ground, more or less, during that eruption. So that's enough material to basically bury the state of Texas about 5 feet deep. So it's a really big amount of area. It all came out of Yellowstone. Okay, so when you take that amount of material out of the ground and you put it on top of the ground, you're left without a whole lot of support for the ground surface, and it caves in. It's what we call a caldera. It's kind of like a giant sinkhole. Now, so these are all the fractures that are associated with the formation of this caldera, and all of this happened 640,000 years ago at Yellowstone. It was the last really large eruption in this particular place. Okay, so moving on. Another thing that was going on at this time, and I'm going to really focus here in this talk a lot on what the USGS did at Yellowstone, also a lot of the other colleagues, but we're here in Menlo Park, and I want to focus on some of the work that's actually been done in this particular location. And these guys right here had an amazing time back in the 60s. On the right is a guy named Don White, and on the left is his protege, Bob Fournier, who's around and still lives in Portola Valley, and we see him pretty frequently. Well, these guys were funded, as was Bob Christensen, by NASA to do studies at Yellowstone. And they got the opportunity to study the geothermal system and to drill 13 science exploration wells into the geyser basins at Yellowstone. The information that they learned, first of all, that would be very difficult to get permission to do today. So we're very grateful to them for what we were able to learn from the work that they did and for the samples that they collected in drill cores that are still preserved today, and we're able to use them because they're sitting in a warehouse in Denver and they're still used today. Anyway, these guys wrote a lot of very classic papers on Yellowstone, and a lot of what we know about geothermal energy production really came from the work that was done at Yellowstone back in the 60s. Here's an example of one of the wells that they were drilling at the time when they were, yeah. Okay, so the next really remarkable thing about Yellowstone, and the piece of recognition that's very important, is that it moves up and down. The ground surface is sort of unstable in that over time it moves. So Bob Smith, who's down here, was one of the party that came in and resurveyed a series of roads that hadn't been surveyed since the 1920s. Dan Jerizian did some work. He's up at the Cascades Volcano Observatory, and he's showing here his tripod that was used for leveling. Well, Bob and his colleagues went and reoccupied all of the benchmarks that were done previously in Yellowstone. And this is a contour map that shows the amount of millimeters that the area had gone up between the 1920s and the 1970s. And in this case, you can kind of make out 500 and 400, and I think there's a 700 is the largest one in the middle. Here's the caldera. And so most of the activity here is going on in the caldera, and the maximum uplift is about 700 millimeters along here in between these two areas that we call the resurgent domes, the area of maximum uplift within the caldera. So 700 millimeters, it's 70 centimeters, it's around 2 feet. And so that had happened in those 50 years. And so this was really a remarkable observation, and is something that we've been tracking ever since, trying to understand this. Bob Smith, by the way, is one of our collaborators at the University of Utah through the Yellowstone Volcano Observatory, and he's been working in a very, very productive career there for many years. The last sort of topic that I want to bring up is the gas flux from Yellowstone, which is something that we didn't know about until about 10 years ago, at least in terms of its magnitude. Here are my colleagues Bill Evans and Deb Bergfeld, who are trying to figure out how much gas is coming out of this particular pool at Terrace Springs. Over here is Cindy Werner. She's now at the Alaska Volcano Observatory, but she did her PhD at Yellowstone using this, an accumulation chamber. Here's an example of some more modern accumulation chambers. And these look at the flux of gas through the soil at Yellowstone. If you have enough of them and you spend enough time in the field, in her case many, many summers, going to many different places and running grids, she was able to ascertain that a very, very high flux of gas is coming out of Yellowstone, on the order of 45,000 tons of CO2 every single day. And that makes Yellowstone one of Earth's most prolific natural sources of carbon dioxide. comparable to a pretty big power plant, coal-fired power plant. Similar to Mount Etna and similar to the amount of gas that comes out at Kilauea in Hawaii. Basaltic magma, that's the kind of magma that gets formed deep down in the Earth's mantle, contains a lot of carbon dioxide when it melts and comes up towards the surface. And so when you see a lot of carbon dioxide, that's a typical thing for a volcano. But again, it's something that we didn't necessarily know was happening at Yellowstone. And by seeing that big number, we kind of equate Yellowstone with some of the other big volcanoes on Earth. Okay, so let's step back a little bit and try to understand now more how all this works on a larger scale. So in this figure, we're looking at Yellowstone. This is a map of the western U.S., and Idaho border is here. Wyoming is sitting out in here, and Oregon out in here, Utah and Nevada. And so this is a feature called the Snake River Plain, which is Idaho Falls and Twin Falls are there. The Snake River runs through it. It's a very, very productive farming country. It's also very flat. Well, underneath that, all that flat terrain is a whole series of old volcanic calderas very similar to Yellowstone. Around 16 or 17 million years ago, there was a rifting in northern Nevada. There was the outpouring of the Columbia River basalts in Oregon and Washington, and there were calderas that were forming in northern Nevada here. And these numbers here, 16, 14, 12, 11, are a progression in the occurrence of these caldera systems that move towards the northeast, towards the present-day Yellowstone. So there's been a whole series of Yellowstone-like features that have existed in the Snake River Plain over the last 16 million years. The North American plate is moving towards the southwest, and so it's overriding an area within Earth's mantle down 50, 60, 70 kilometers. Kilometers, by the way, 0.6 miles. I'm a scientist. I tend to use the weird metric units a lot. So please divide if I don't translate it into English. In any case, so the plate is moving this way, and it's moving over top this melting anomaly in the mantle. And so we have a progression of younger and younger caldera systems ending up with Yellowstone today. This is what the Snake River Plain looks like. This is actually from the craters of the moon. And so it's very, very flat. This is what Yellowstone will look like a few million years from now. Eventually, it's going to cool down. The land is going to subside and sink. We're going to continue to have outpouring of mantle rocks, but not as much melting of the upper crust, which happens at Yellowstone today. It'll get all buried up and flattened, and they'll be growing potatoes on it. This is an example of seismic tomography made of the Yellowstone plume or hotspot region. In this case, we're looking down. Here's the surface of the Earth, looking from Yellowstone way out towards California. Yellowstone, Snake River Plain, Basin Range, Sierra Nevada, and Central Valley. So this is now looking at a slice down into the Earth. This is in kilometers here, so 200 is on the order of 100 miles deep. And the colors represent the velocity of seismic waves that are moving through the crust. To make these diagrams, you're looking at earthquakes that are happening across the globe. And you're looking at what regions the rays from the earthquake come up quickly and which ones where they're delayed. And they're able to put together these maps and show that the land beneath the Snake River Plain, the mantle of the Earth beneath the Snake River Plain, is slower. The earthquake waves move slower through that region, and that's either because it's hotter or it's partly melted. And that's not something that you see, for example, over the Central Valley. This is an area that's fairly unique, and we have a lot of melting going on, and that ultimately is what is producing basaltic magmas similar to Hawaii that are coming up to the surface beneath Yellowstone. Here's another cross-section, again, where you're looking in depth. So this is to basically the base of the crust beneath Yellowstone, 40 kilometers, something like 25 miles. You have the basaltic magma that comes in. Again, that's a liquid magma, is molten rock. It's coming off the mantle. It's rising into the crust. The crust of the Earth is less dense, and it's contained of materials with higher amounts of silicon dioxide. It melts fairly readily. You mix what melts in the crust with what's coming from the mantle, and you eventually create magma reservoirs high up in the crust that are less dense than the materials that are coming in from below, and they're also thicker, they're more viscous, and much more explosive. And so that's how you get these accumulations of fairly explosive magma up in the crust down at 5, 6 miles depth beneath Yellowstone. Okay, so let's talk a little bit about some of the hazards at Yellowstone. In this whole series of slides, I've got this blue dot that sits over, and it moves around, and it's going to move eventually over from low-frequency events to high-frequency events. Low-frequency events might occur every 100,000 years or every million years, and an example of those would be the big volcanic eruptions at Yellowstone, these caldera-forming eruptions. There have been 3 remarkable ones, and there is ash that can be found from these events as far away as Texas. So they're putting ash high up into the atmosphere, into the stratosphere, and it comes down a long ways away. So these are big events, but Yellowstone may be done with this particular type of event. There's no reason that it has to ever happen again. Volcanoes do live and die eventually, and so Yellowstone may have sort of finished the amount of highly silicic melt that it can extract out of the crust. But it is also possible that we could see another one of those eruptions at some time in the future. But in general, they're very, very rare events, not only at Yellowstone, but around the world. Just to give you an idea of what might happen if this ever did happen again, in that very, very unlikely case, one of my colleagues at the Cascades Volcano Observatory, Larry Maston, has done some simple modeling using wind patterns that we have available to us and tossing ash from exactly replicating the Lava Creek Tuff eruption. In this case, he took wind data from 2006 and a specific week, April 21 to April 27th. He put Lava Creek Tuff size, 1,000 or 300 cubic kilometers of material up into the air and allowed it to settle out with the wind patterns that were present. And you can get an idea of what would happen, at least just from the ash fall of one of these events. There's some fingers coming out above the Great Lake. But this is 1 to 3 millimeters of material. So even though you hear about how these are enormous events, most of the material is falling out either within the caldera or areas immediately east of Yellowstone. Now, you can choose another week, for example, and you get a fairly different result. So every single week that you could possibly have an eruption, you're going to get a different event. You can't just say this would happen, because it totally depends on what's happening in terms of how the volcano erupts and the amount of time that you would take and the specific wind conditions during the time period that you're erupting. In this particular case, you get some fingers of 1 to 3 millimeters of ash that make it as far as the Great Lakes and over here almost into New York State. But for the most part, the eastern U.S. doesn't end up getting a lot of ash, even from a giant eruption such as might happen at Yellowstone. But these eruptions in the past have a remarkable effect on the landscape. And so here is the Rocky Mountain area. Yellowstone Lake sits right here. Here's the Yellowstone caldera. There's the Grand Teton Mountains. And you'll see the Tetons march up here. There's all sorts of Rocky Mountains, the Gallatin Range, the Absaroka range up here. But there's no big mountain ranges within Yellowstone itself. And that's because during these big caldera-forming eruptions, especially the first one and the third one, the mountains eventually, they fall into the caldera and they disappear. And then later on, new lavas come out of the ground and bury a lot of what was present in terms of the landscape. So definitely, these are big events and they have big impacts. And the reason that Yellowstone looks like it is because of its geological history. Okay, so now here's a slide that shows you the park boundary. Again, it's on the order of 100 kilometers or 60 miles by 60 miles. Here's the caldera, which we've seen several times now. Here are the pink roads that run through the park. And right now I'm going to show you what things looked like immediately, or everything that's happened at Yellowstone within the caldera since the last caldera-forming eruption. So all of these are lava flows. They are, in some cases, very big lava flows, and they bury the topography, and they flattened out the topography that you would see at Yellowstone. This is one of the larger ones. It's called the Pitchstone Plateau, and it's about the size of Washington, D.C. It's anywhere from 50 to 300 or 400 feet in thickness in places, and sometimes even a little bit more. And it's 70,000 years old. So this is actually the last volcanic eruption at Yellowstone, is this 70,000-year event. Since that time, there has been no volcanism at Yellowstone. But all of these lava flows came out since the last explosive eruption. So a lot of times you'll hear, if Yellowstone erupts, this, and they'll talk about the worst-case scenario. But this is what's been going on for the last 30 or 40 big eruptions at Yellowstone. And then there's also a whole series of eruptions. So this, if you've been to the Grand Canyon of the Yellowstone, you were looking at one of these post-caldera lava flows. If something like this came out today, it would be a big deal within Yellowstone National Park, but it would not have a lot of explosive activity. It wouldn't cause really a national scale emergency. It would be very much a local event, but it would still be a very spectacular thing. Okay, another thing that's happened since the last caldera-forming eruption is all of these yellow lava flows that have come out of the ground. And these are all basaltic lava flows. These are the sorts of things that are created in the Earth's mantle. Normally, if they come up beneath the caldera, we have all of this silicic magma reservoir, the stuff that forms the explosive eruption. It's high up under the ground, and it doesn't allow the deep magmas to come up and penetrate through them. So they pond below, just like in the figure that I showed you a little while ago. Outside the caldera, though, the crust is cool, the rocks can break, and the basalts can come out and form nice little flows, like you'd see at the Sheep Eater Cliffs. And this is an example of what one looks like in Hawaii. You can imagine what it would be like at Yellowstone if it came out and formed one of these nice lava flows. So these events occur more on the order of every 10,000 years. They actually appear in groupings. The last one was 70,000 years ago, so they don't always occur every 10,000 years. There's been about 80 eruptions at Yellowstone since the last caldera-forming eruption, and the most recent was 70,000 years ago. Even more frequent are hydrothermal explosions. These are systems where the geysers, the hot water system that underlies Yellowstone, becomes unstable, and the water flashes to steam and throws rocks out onto the surface and can create fairly large holes in the ground. This is called Indian Pond. It's about 1,000 feet across. It formed 4,000 years ago. There are a lot of these events that occurred in the last 15,000 years ago at Yellowstone. The largest of them forms Murray Bay within Yellowstone Lake, and it's 2 miles across. So if you think about the way that geothermal systems are established, if you drill into a geothermal system, the boiling temperature of water at the surface is 100 degrees C, right? At Yellowstone, you're at a higher elevation. It's actually more like 92 degrees centigrade, or about 200 degrees Fahrenheit. But as you go down in the ground, the pressure's increased, and the boiling temperature increases just as it would in a pressure cooker. And so the temperatures actually below Yellowstone, once you get a few hundred feet down, are much, much higher than they would be at the surface. So if you're able to depressurize that system, you'll take water that's way above its boiling point at the new lower pressure, and it'll catastrophically explode into steam, breaking rocks along the way and forming these very interesting landforms. Here's an example of what one looks like at Biscuit Basin, and this is one that a whole field trip of geologists were witnessing. The park geologist Hank Hessler and Bob Smith from Utah were there to witness this at the time. This is not a big one, but this gives you an idea of what one might be like. And here is an example of where these hydrothermal explosions are located at Yellowstone, in all post-glacial, so all in the last 15,000 years. A lot of them near the north end of Yellowstone Lake, forming holes that are in the ground that are fairly large. And so this is a hazard that definitely is present at Yellowstone today in a more frequent basis than something like a volcanic eruption. Okay, now I'm just going to show you another series of slides here. These are faults, so areas that have broken rock. These are associated with the resurgent domes where the caldera moves up and down. These are associated with tectonic movements associated with the Tetons, and there's other earthquake faults out in this direction near Hebgen Lake. Here's where a lot of the earthquakes have occurred at Yellowstone over the past 25 years, just a representative sampling. You'll see there's a lot of earthquakes out here near Hebgen Lake, and that's probably because it's close to the region of the magnitude 7.5 earthquake that occurred in 1959. I'll talk about in a moment. But there's earthquakes all around the caldera as well. Most of the earthquakes are small. They're magnitudes 1s and 2s, occasionally 3s. Most of them are not felt. Occasionally there is a big earthquake. And there might be a big earthquake somewhere in the Yellowstone area every 100 to 300 or 400 years. The last really big one was this magnitude 7.5 in 1959. It occurred out at Hebgen Lake. It's outside the park. Caused a big landslide that buried a campground and killed quite a number of people, around 20 people. And here is a slide from Bob Smith showing the offset, the actual scarp that was formed from breakage of this fault. It's 3 geology students tall in this case, so it's pretty sizable earthquake. So this is, again, a geologic hazard that's much more present in the area than volcanic eruptions, something that's definitely something that the people who live around that area need to be a little bit more familiar with. And here's some photos from the 1959 earthquake. Okay, monitoring Yellowstone. Well, you've gotten the picture probably by now that Yellowstone does have a lot going on in it. It's a very active place. It's got all sorts of activity. We have a volcano observatory there, partly because we feel we need to keep an eye on it because it does have this sort of big hazard that's a possibility there, but also because it's a globally unique place. There is no place on Earth that's quite like Yellowstone. It has this big magma system, and there's constantly things happening there. And so we feel that it's really important that we as scientists know what's going on there and can present that data and publish it for our colleagues all around the world, because what we learn at Yellowstone really teaches a lot about volcanoes everywhere. A lot of volcanoes don't do anything. They sit there not having any activity at all until about 2 weeks before they erupt. Yellowstone, we're constantly seeing activity, even though it hasn't erupted for 70,000 years. So it's an interesting place to do work. We have a volcano observatory that's set up to look at Yellowstone, and it has 8 member institutions, the USGS, who runs the other volcano observatories, but also Yellowstone National Park. The University of Utah runs the seismic network at Yellowstone and has for over 40 years. And they're very active. They receive a co-op through the USGS to work there. There's also the University of Utah, the 3 geological surveys of Montana, Wyoming, and Idaho, and UNAVCO, which is an organization that runs through with a contract from the National Science Foundation to run a lot of geophysical equipment, some of which we have at Yellowstone. So we all work together. It's a virtual observatory. There's no buildings that we have at the park. We go to Yellowstone, we collect data, we have data that's streaming over the internet that we all get a chance to look at, and you, in fact, can all look at it too, because it's all available for the public. Here's an example of our seismic network. There's around 30 seismometers spread around the park. When you have a seismic network, you're able to locate earthquakes. You're able to find out where they're happening, how deep they're happening, and how large the earthquakes are. This is an example of the earthquakes that occurred at Yellowstone last year. There were about 1,900 earthquakes. In this case, they're sized by the magnitude, so you can see most of these earthquakes are much too small to be felt, magnitude 2s. There's maybe 4 or 5 last year that were felt. They're color-coded by time, and so you can see that different groupings of earthquakes occurred at different times. The blue ones were the earlier ones, such as these ones that were near West Thumb. This yellow one occurred later in the year. Some of these red ones occurred around in December. These are all little earthquake swarms. And it turns out that about half of the earthquakes at Yellowstone are in these swarms. They're little groupings of earthquake. An area might become overpressurized, and the earthquake swarm relieves that pressure in that particular area. And it's very common, so we'll get maybe a week that goes by where we'll see 50 or 60 earthquakes in one particular area, and then we won't see any more earthquakes for the week after that. Another thing we have is GPS monitoring. These are fancy GPS receivers that are attached to monuments, and so the monuments don't move anywhere. Again, we have well over 20 GPS receivers that are run through UNAVCO, and the next data I'm going to show you is from the White Lake area here on the eastern part of the caldera. And so here you can see one data point for each day. We actually get data out of these things every second. But we don't always look at that data. We average a day's worth of data. And in this case, you're looking at the time from 2005 all the way to 2014. And you can see that this particular station was moving west. It was moving south. And so southwest is the direction that all of North America in that area is moving. It's just moving along with the rest of the continent toward the southwest. But it's also moving up and down. From 2005 to 2009 or 10, it was moving up, and in this particular case, moved up about 20 centimeters or something like 8 inches, 25 centimeters, something like that, and then started going down in this time period here. So the great thing about these GPS receivers is they allow you to look really, really in great detail at one spot. And we have 20 or 30 spots, so we can look at 20 or 30 spots with great detail. We look exactly what's happening, and you can get a feel for day-to-day variations. If something starts happening, you go to the GPS, and you can see if the ground surface is moving up. We have another technique that's called INSAR. It's another satellite-based technique like GPS, and one of the people who works on it is Chuck Wicks here, who's a scientist in Menlo Park, and he produced this particular image, and it's called an interferogram. Now, INSAR is a radar technique, and you have a radar that's up in space, and it's taking an image of the land surface below, and it's scanning the land surface below. In this case, you'll take an image that you did in 1 year, say in this case, I think it was it was maybe 1995 to 1997, so 2 years apart. And you're looking at how the ground surface changed in elevation relative to that satellite. And what you get here is, it's like a contour map. So any yellow ring, for example, is going to represent areas that moved up a similar amount towards the satellite during that time period. Same goes for this yellow ring or this pink ring. And when the rings are really close together, that means that there's a lot of movement in that particular area. So here, in this 1996 to 2003, there was about 12 centimeters of uplift over that time period, something like this amount, over a very large area, about 5 miles across. So that's a lot of volume increase. And it dies off when you get to this area out here, sort of in the middle of the caldera. So this is another way, instead of just looking at that spot and that spot and that spot with GPS, you might sort of get a feel what's happening, but you look at a map like this and you really get an understanding of sort of on a map view what's happening and where is the ground deforming and where is it moving up. If you don't understand that, we can talk about it later on in the questions. I kind of can't get in too depth on each single slide, but I'm trying to make it so that it's understandable. Another satellite technique that we use looks at heat flow. This is Greg Vaughn, who works at the USGS in Flagstaff. He uses the Aster satellite, and he can specially send it to look at Yellowstone at night when the sun's rays are no longer heating the ground, and look at those areas that are hot and those areas that are not as hot. And so some of these areas only have a little bit of an anomaly. Some of the areas have a lot of watts per square meter. A lot of energy is coming out of the ground, such as the Sulphur Hills here, or areas within the Norris Geyser Basin. And so this is another technique that we can do every 10 years or so and compare if things are changing within the park. And we can also use some other satellite-based techniques as well. A couple other techniques we have. We look at river discharge and temperature. We look at some geyser behavior. We look at geophysical things like tilt and strain. Right here I have a couple images that look at temperature and water flow. In this case, it's related to the eruption of Steamboat Geyser. The Yellowstone's tallest geyser sends water up into the air about 300 feet, and this is close to it in this particular image taken in 2005. Well, last summer, Steamboat erupted. And you can see that here. This is a temperature gauge that we have right in the outlet, right below the geyser. And here is time on the bottom. And right there is when there was a big spike in temperature, about a couple hundred feet away from the geyser itself in the outlet channel. And you can also find that about a mile away, and maybe about an hour later, there was a big pulse of water that came out the discharge through a stream gauge at Tantalus Creek. So this is discharge here versus time. This peak lines up with this peak. And another neat thing that you can see from this particular diagram is that before the eruption, there were all these tiny little peaks, which represent small eruptions of steamboats sending water maybe 15, 20 feet in the air. As soon as the big eruption occurred, where the water went off for an hour and hundreds of feet into the air, nothing came out of the geyser anymore. So all you see here is a nice flat curve that represents the daily variations in temperature that you would normally measure in any creek. And so that's the kind of stuff that you can learn from these sorts of data that we have streaming in the internet and you can look at every day. Okay, the next series of slides, I'm going to talk a little bit about what's been happening in the last 10 years at Yellowstone, some of the more exciting things that we've been noticing. First one I'm going to talk about is the Denali earthquake. Then we'll talk a little bit more about uplift in the caldera, going up and down, some of the disturbances, hydrothermal disturbances, the hot temperature in water at the Norris Geyser Basin, and some swarms that occurred in the last few years. This part's a little bit more technical, but we'll try to stay with me. The Denali earthquake occurred in 2002, and it was a magnitude 7.9 that occurred on the Denali Fault and up in Alaska. Anytime you have an earthquake, especially on a strike-slip fault, you'll get surface waves produced. Those are the ones that do a lot of damage to buildings. And in the case of this particular earthquake, it sent big surface waves out in the southeasterly direction. Now, every one of these little diamonds here represents a seismic station. And the ones that are red are pegged out. They're clipped data because the ground movements, the surface waves that were coming from that, associated with that earthquake, were so big, even down in Montana and Wyoming, that the seismometers couldn't record the data. There was too much shaking coming in, and so they're what we call clipped. Whereas the blue stations, there was a little bit less ground surface wave movement down in California, for example. These are figures from a paper by the University of Utah group, and Stefan Husen was the main author. And this one on the right, you don't really need to worry about too much, but it's calculating the stress level that was coming associated with these surface waves. Well, when the ground shaking got to Yellowstone, it set off earthquakes all over the place at Yellowstone. They were small earthquakes, magnitudes 1s and 2s and 3s, but some of them were felt. And this is a remarkable example of something that wasn't even known about until the early 90s, and that is the phenomenon of triggered earthquakes. That you could have an earthquake in one location on the Earth, and that the waves that move around the Earth are actually triggering earthquakes in other locations, although much, much smaller earthquakes in these distant locations. And so you can see here that most of the events were actually within the first couple hours of the Denali earthquake surface waves hitting Yellowstone. So it also indicates just how pressurized and ready for earthquakes Yellowstone is, and how easy it is to set off Yellowstone, at least in terms of producing earthquakes. Another thing that happened back around that time was there was a lot of hydrothermal activity in the Norris Geyser Basin area. There was a new linear vent that formed at Nymph Lake, formed some really, really loud jet-like thermal features. A lot of trees died in the area in that time. The park geologist, Hank Hessler, spent quite a bit of time documenting the changes. Later that summer, there was a whole region in the Norris Geyser Basin, in the back basin, where there was anomalous activity in a lot of the geysers there, and there was ground temperatures that were increasing greatly, and a lot of pools that were turning into steam vents or fumaroles. Here's an example of a thermal image taken on the trail, and you can see that some of the temperatures right on the trail are hitting above 50 degrees centigrade. There were measurements taken right off the trail that were the boiling temperature of water. So if you were walking barefoot, you would have been pretty uncomfortable. But the Park Service closed off the back basin for a period of about a month, and things cooled off and went back to normal. A final thing that happened in this time period was Steamboat Geyser. It went off 6 different times in the period between 2000 and 2005, with most of them happening in 2002 and 2003. Then it went to bed after 2005. It didn't erupt again until this last year. And there was our colleague Chuck Wicks. I showed the picture of that interferogram showing the area in the northern part of the caldera that was experiencing uplift. He hypothesized that maybe the uplift in that area, there was some magma maybe coming in at great depth, and it was pushing up on the crust, and that causes a little bit of tension at the surface, and maybe that was enough to allow more of the deep thermal fluids to get out and cause some of the ground heating and some of these other strange behavior. And he may well be right. We don't know for sure, but what we do know is that when deformation in that particular area stopped, we stopped seeing a lot of the strange hydrothermal activity. So we'll probably want to see a few more cycles of this before anybody will really believe it, but interesting observation. So this is another one of these interferograms produced by Chuck Wicks, and it shows you what happened after this area up here that I showed you earlier stopped rising. In this case, the main caldera started to go up. So again, we have this bullseye area. The maximum uplift is in the center right here. It falls off as you move to the edge, and actually the area near the Norris Geyser Basin in the northern caldera is going down during this time period from 2004 to 2009. So this part now goes up. The part that had been going up before now is going down. And this is really an immense amount of uplift, especially when you consider how big the area is, something like 30 miles across. All of that area going up as much as 25 centimeters or even 20 centimeters. It's a big volume change, and probably because there's some magma coming into the system at depth and is pushing the ground up a little bit. So there's some uplift. It went on to 2009, but eventually it stopped. And one of the interesting things is, and this has been noticed several times now, is that the uplift often stops when there are big earthquake swarms. So the earthquake swarms appear to be relieving the pressure on the system. You have uplift, things are gradually moving up. You have the earthquakes, and things start to settle again. These are seismograms. This is from one seismogram. This is from a different location at the south end of the lake. This is from the north end of the lake. All of the data are for the 27th of December, 2008. These again come from the Yellowstone Seismic Network. In this case, you have time represented starting from early to late. Each 15-minute period is one line, so 15 minutes, 30 minutes, and you're moving through the day, so 4 of these would be an hour, and you're seeing earthquakes. This blue up and down is an earthquake. When you're on the black line, the earthquakes are all black. When you're on the red line, the earthquakes are all red. Every time you get this squiggly stuff, that means that you're looking at an earthquake. So in this particular day, you had a lot of earthquakes. And the biggest one was a magnitude 4. There were also one here, 3.5, magnitude 2. There were a number of felt earthquakes. This happened in December. There weren't a whole lot of people around Yellowstone. Yellowstone's pretty cleared out. But there were maybe 15 or 20 people who were living at lake at the time, and they were feeling many of these earthquakes. It happened for about 2 weeks. The data were later reduced by Jamie Farrell, who's a PhD student, now finished at the University of Utah. And here are a couple maps that show you what was happening during that period of time. Turns out that the earthquakes were on a sort of a linear trend. This is the map view. They started, the blue is the early earthquakes, the red are the latest earthquakes. They started to the south, they slowly moved north. This is another one of these cross sections. Now you're looking down into the crust, 10 kilometers deep, south over here, north over here. The biggest earthquake is down at depth. And as time moved on, the earthquakes moved more and more towards the north, and there were fewer and fewer deep earthquakes. This was a pretty nervous time for us, not only because there were a lot of earthquakes, but because people get rather agitated when things are happening beneath lakes. Lakes freak people out because you can't see what's going on. You can't see that nothing's happening. And so people just hypothesized all sorts of crazy stuff. I mean, it was a very, it was a nervous time because there were a lot of earthquakes going on, but there were never any steam explosions, never anything happening other than just these small earthquakes. So, then there was another earthquake swarm, and this was the next year in 2010. In this case, instead of over here by the lake, we had an earthquake swarm way out here on the western side of the caldera. And this was about 2.5 times more earthquakes, about 2,500 earthquakes over a 2-month period. Most of the earthquakes were within the first few weeks. People didn't seem to get as nervous about this one, again, mostly because it wasn't under a lake. And it was in an area that was just a big lava flow. There wasn't anything terribly interesting out there on the Madison Plateau. But it still turned out to be a really interesting series of earthquakes. And our David Shelley, who works here in Menlo Park, just published a paper where he used some interesting techniques called waveform-based detection and relocation. So normally, if you're measuring earthquakes, you have a big cloud of earthquakes, and you can't really make out how they're all related to each other because they're using data from seismometers that are really far distant from each other. If you really focus on just a couple really good sets of data and you use relative locations, you might not really get a great you might not get an accurate location for any particular earthquake, but you can look at their relative locations. And so that's what he did. And so I'm just going to show you a little movie that represents the earthquakes. And in this case, there's about 8,700 events that he's able to detect, way more than you can get with the seismic network itself. And you can make a movie here. And you see that all of those earthquakes are aligned on a single fault that's dipping to the east. So they're on a plane, and all of these earthquakes are happening. Okay, I'm going to take it and bring it back. So here you can see they're all on a nice plane, and that plane dips to the east. Now the colors here represent different times of the earthquake. So the blue ones are early, down the 18th of January, and the red ones are happening later. All right, and then when we move a little bit further along here, everything turns red, and we'll start them, and you can watch the earthquakes happen. And once they're done, they'll turn blue. And you can see that there's little squirts of earthquake that are happening along this plane. And the thought is that there are fluids being released, and they release from one part of the fault, and they basically lubricate other areas of the fault and allow additional earthquakes to nucleate or occur. So that's just a neat little example of sort of how some of these things work. Okay, so now it's time for questions. I made questions first because I have questions that I get asked all the time, and I figured, you know, I'll just cut to the chase and I'll answer some questions. You can ask questions later on. Okay, so when will Yellowstone erupt again? Somebody was going to ask that, right? And the answer, of course, is we don't really know. It hasn't erupted for 70,000 years. Even when we had these really immense hydrothermal explosions back in the post-glacial times, 5,000 years ago, there was never any evidence that there was magma involved in those events. If it does erupt, you know, it could erupt. It could erupt next year, but probably not. I don't expect it to erupt within my lifetime. But at some point in time, again, it will erupt. It just might be 1,000 or 10,000 years from now. What will the eruption be like? Well, you know, there's an outside possibility that it'll be one of these super eruptions, but that's by no means the most likely scenario. And as I said before, it's perfectly possible that there never will be another super eruption out of Yellowstone. We'll get one somewhere on Earth, and but Yellowstone's already had 3 pretty big eruptions, and most of these volcanoes don't have 4 or 5. They kind of use up all of the crust that's available to melt, and they lose their ability to keep creating really big eruptions. So more likely is we'll have more of these big lava flows coming out, sort of using up what magma's down there. But nobody can tell you for sure. Is there enough magma down there to create a super eruption? So a super eruption, again, is one with 1,000 cubic kilometers of material. Well, to get a super eruption, you have to get all of the melt into one place, because these eruptions generally, down there it's like a sponge. It's a magma chamber. The sponge, the green stuff of the sponge, the animal part of the sponge, is crystals. It's rock. And in the pores, that's where the melt is. But you can't erupt a magma unless it's more than about 50% melt and 50% crystals. Most volcanic eruptions are like 75% melt. Now, all of the images that we have through the seismology, through the tomography, and the example of the image I showed earlier, tends to predict that there's on the order of 10 or 15% melt down there on a broad basis. We can't really image small areas. So it's possible there's some highly molten areas down there, but they're probably not enormous. So we don't think there's a big enough area with highly melted regions that could create one of these big eruptions. But there could be smaller areas. So there's probably areas down there that could erupt if the right circumstances forced it. Has the magma chamber gotten bigger? Well, this is something that came into the news recently. Our colleagues at the University of Utah have redone their tomography for the magma chamber beneath Yellowstone. And that's something that's going to constantly happen because we're always getting better data. We have new equipment in the ground. We're able to put things in better places so that we have better coverage. And so they were able to do some work and to find that compared with the last time they did tomography, they were able to see the magma better. So they got 2.5 times more magma down there than they got the previous time. The number is still consistent with what we see. It's consistent with the size of the caldera. It's consistent with the amount of heat coming out of Yellowstone. So it's nothing shocking. It just means that we can do our job better than we could a little while earlier. And 5 years from now, there will be a new study that comes out that figures things out a little bit better, and that's the way science proceeds. Will we know it's coming? And this is a tough one to say because nobody's ever seen a super eruption. Nobody's been around. The last one was 26,000 years ago, and they took really lousy notes. What do we, we have seen some relatively large eruptions, but the last big eruption on Earth, sort of even a tenth of the size of one of these, was the Tambora eruption in 1815, caused the year without a summer. And that was a very big eruption and would really cause a lot of havoc, even though it's only a tenth of the size of one of these Yellowstone eruptions. But we don't have a lot of data on exactly what happens before them. But we do know what happens before smaller volcanoes erupt, and we know what we think would happen at Yellowstone. And we also have watched things happening at Yellowstone now for 100 years. We know earthquakes happen all the time. We know ground deformation happens all the time. They really have to happen in a bigger scale. So if we're going to see earthquake swarms, they're going to be big, and they're going to have some larger earthquakes to break the rock up so that we can get magma to the surface. You're going to see ground deformation in the same area that you're seeing the earthquakes. That's something we really rarely see, especially significant amounts of ground deformation on the order of meters of uplift in a year or so, really showing that something's moving. You're going to see increased gas emissions, and that's going to be obvious no matter what techniques you have there. And you're also going to see, if magma is getting towards the surface, it's going to cause additional steam explosions. It's going to, magma hits a boiling aquifer system, boiling groundwater, it explodes. And so you're going to start to see all of these things happening at the same time. The last time there was a big eruption at Yellowstone, 640,000 years ago, there was a whole series of lava flows that came out around the periphery of the caldera before the big eruption, maybe 10,000 years before. Here we haven't had anything for 70,000 years. That's not saying for sure we're going to get the exact same thing and we can all not worry about it, but it just goes to show you that a lot needs to happen before a big eruption. So that's all I have prepared, except to show you that we do have a really good website and has lots of articles, provides a lot of information on what's going on at Yellowstone, all the data that you might want to see. It's really easy to find. You just Google YVO. Another thing is we have some fact sheets. I think we brought a few of them in. Leslie brought them. They're gone now, but these things are all downloadable, and they're pretty nice 6-page and 4-page glossy brochures that you can print out for yourself. And they talk about a lot of the things that I brought up today. So thanks, and I'll be happy to answer some more questions.